Hey everyone, I'm happy to introduce Sham Kakade today. He's currently at a combination of University of Washington and Microsoft Research and possibly other places. He with stops along the way in places like Caltech and Gatsby and Toyota Technology Institute of Chicago, all great places. Sham's talking about reinforcement learning today, but I've seen his work sort of appears and has been influential all over the place. Things that pop to mind include like spectral methods for estimating latent variable models, automatic differentiation and when you can do that, and a bunch of learning theory stuff. He's won awards like the ICML Test of Time Award and so on. So I'm excited to hear the talk. I'll let you take it away.
Okay, great. Thanks, Mark. Yeah, it's a pleasure to be here, and it's too bad I couldn't be there in person since it's I don't think it's such a far drive from Seattle, but yeah, it's a pleasure nonetheless. Today I'm going to be talking about policy gradient methods, and in particular, they really provide the backbone for a number of successes in reinforcement learning applications. And because we tend to believe that reinforcement learning is going to be an important component in deployed machine learning applications, we really want to get a handle on some of the fundamental statistical and optimization-based approaches in this area. And part of the reason RL is so important, just thinking more broadly, is machine learning, ultimately, we need to deploy it in interactive environments. And as we do that, reinforcement learning and Markov decision processes provide one of the most natural paradigms to model the types of problems we face. So I'll just quickly give some notation and the MDP setting. So MDPs, I think some of you are familiar with them, but let's just go through the setup and the notation. So we have some agent. The agent has a policy or a behavioral policy, which is a mapping from the system state to the action it takes. So say at time t, it takes action AT. That action will impact the environment. It might have a force. That force will change the system state, and it'll receive some reward or cost based on the action it's taken. And we'll think about a setting where we start at some state as 0, or maybe there's a distribution of initial states. But we're going to execute our policy for some number of steps, and we'll see this observed trajectory of state actions, rewards, and so on. Okay, and we could look at undiscounted value functions or discounted value functions. So for the purpose of this talk, it's more natural to deal with the discounted case, where we're going to measure our long-term success by the sum of the discounted future rewards, starting at S0 when we take policy pi. Okay, and our goal is to find a policy pi which maximizes our long-term future value. Okay, so just bumping up a level. So since I can write here, I'm also very happy to take questions along the way once we get into the meat of things, because it'll make it a little more fun and more interactive. And if people want to share the videos, I'm always happy to see more people. It's nice to recognize some more faces. It's really up to you, but if you want to share your video, by all means. Okay, so right now let's just set up some of the challenges we face in the setting before we jump into various details. So what are the challenges we face in reinforcement learning? So we look at this toy example. We have a little robot here that is wandering the world, and one of the challenges is this robot might not know the environment it's in. So we have to deal with exploration. There's this credit assignment problem that maybe we got a -1 reward. What action in the past was responsible for getting this? It might have been going down this direction, which caused the problem. So we don't get immediate feedback as to what the right thing to do is. So on top of all of that, in real reinforcement learning problems, we want to handle the fact that we have a large number of states and a large number of actions, possibly infinite set of states. States you could think of as the joint configuration, the angles, and so on. And it could also be the cube configuration. Our actions could be the forces that we're going to apply at these different actuators. Okay, so before we start looking at this particular optimization approach, let's just step back a bit and think about how to think about some of these issues in reinforcement learning more generally and how they compare to supervised learning, because there is a real sense in which the optimization problems we face in RL are fundamentally different than those we face in supervised learning. Okay, this is an informal claim, but I think there's ways in which you can formalize it. So before jumping into this comparison to supervised learning, let's just look at the classical approach, which is these tabular dynamic programming approaches. So, think about, let's take this running example of this this dexterous robotic hand manipulation. So we've got our system state, we've got the action we apply, and one of the classic algorithms are these iterative approaches. So this will be, say, the policy iteration algorithm. What we're going to do is we're going to start with a policy and greedily try to improve it. Okay, so what we'll do is we'll start with a policy. We'll compute this Q function. You can think of this as a one-step look ahead, which means we're at state S, we take action A, then we follow policy pi onwards. Okay, so we're deviating from what we're currently doing and seeing how well we do in the long run. Okay, so we're going to compute that. And we can compute that at every row in the table, which obviously this is not feasible because of the size of this table. But suppose we did that, then the next thing we would do is we'd update our policy to be greedy with respect to this. Okay, and classical dynamic programming theorems show this does converge globally to the right answer. Of course, this table is large, and on top of that, we might not even know the dynamics model, so we might not even be able to compute things like this. Okay, so how do we handle this issue? And this is really a question of generalization. Okay, this is what we think about all the time in machine learning, that we have this infinite table. We're only going to observe various rows and possibly not even the Q functions. It depends what approach we're using, but we're trying to generalize from the finite number of samples we've seen to deal with this possibly uncountably infinitely large table. Okay, and in particular, deep learning approaches are particularly appealing here because they seem to be one natural approach that works very well for generalization. Okay, so in a sense, this space of RL and deep RL, we can really think about it abstractly as we're trying to handle the curse of dimensionality in dealing with these large problems. Okay, but the challenges are different. Okay, so that's this sort of tabular dynamic programming approach. In practice, we tend not to do that. In most state-of-the-art applications, there's some loop which is just directly do gradient descent on the objective function of interest. So you take a behavioral policy, you parameterize it by a neural network. It could be stochastic, because if you've got discrete actions, parameterizing the policy with a stochastic policy allows it to be differentiable. And in most of these applications, we just do gradient descent with definitely lots of under the hood tweaks to get it to work. But let's go ahead and ask ourselves, what are the things we like about this approach? Okay, well, the great at dealing with the large state and action spaces, because that's directly handled by the neural net parameterization. The way we're acting is not a big table. It's some parametric functional form mapping the input state, possibly features of the history, to a distribution over actions. They're nice because we can estimate these gradients in a Monte Carlo way. We don't necessarily need to know the dynamics in the world. We can actually just behave according to our stochastic policy, and we can get unbiased estimates of this quantity with simulation. So this is also nice that we could possibly actually just run this without a dynamics model. And on top of that, one theme we know in machine learning and in supervised learning is it's a pretty darn good idea to try to optimize the cost function we care about. There's been, all other things being equal, we always want to start by trying to directly go for optimizing the thing we care about. And that definitely is the spirit of these approaches. Okay, so these points, obviously this point, we don't have the analog in supervised learning, but certainly in neural nets, this first point is directly analogous to supervised learning. This is also largely analogous to supervised learning. Maybe we can't directly do 0-1 loss, but there are relaxations which are almost the same. Okay, so now let's try to get a handle on some of the differences between this approach in reinforcement learning compared to supervised learning. Okay, so in supervised learning, if we put our practical hats on, we know that when we do these deep learning methods, we have a non-convex optimization landscape, and to a large extent, it doesn't really bother us. We just do stochastic gradient descent, maybe with various tricks, but it seems to work pretty well. Almost out of the box, not quite, but it seems to work pretty well. And to a large extent, practitioners aren't so concerned about non-convexity. And there's some theoretical evidence that supports this, that maybe the saddle points and the types of places we get stuck in supervised learning problems, they tend to be easy to escape from. Okay, so the claim is that reinforcement learning, this is not the case. Okay, so in reinforcement learning, it's actually very easy to see that there are real RL problems, pretty much all of them, that we often actually have extremely flat regions where the gradients truly are vanishing, and this isn't easily fixable with things like dropout, adding noise. Okay, so intuitively, why is this the case? Think of a robot that maybe it has some legs and arms, and the goal is for it to stand up, but you only give it a reward when it stands up. Okay, so when you start the system, you're going to drive the robot randomly. Okay, and when you drive it randomly, it's never going to get the reward, and the gradient is flat. Okay, there's no easy way to fix this when you just start it randomly. So you truly get these flat gradients, and formally, from a precise perspective, you can translate that these flat this issue into actually showing that not only is the gradient flat in terms of its second order curvature, that this problem in RL you can really view as flat gradients to very high orders. So consider this very simple problem. Just make a formal statement here. Think of this very simple problem where we've got our agent. It can take 2 actions to the left and 1 to the right. Okay, there's a reward at right over here, and no rewards in between. If we start the system randomly and try to do gradient descent, say it's on some complete policy parameterization where we can represent every policy, our gradient is basically flat. Okay, why? Because it's exponential time to hit this goal state, because we have a random walk with a drift moving left. Okay, so that flatness really translates into not just having flatness in the second order derivatives, but really to almost the length of the chain. So this really should be an S here. But essentially almost to order S derivatives, they're exponentially small. Okay, so we said that, look, these gradient methods are one of the tools we use, but how do we start thinking about them? What are the secret ingredients to get them to work? And how do we start thinking about these flat gradient issues? But at least from this kind of bird's eye overview, we see that the way we think about these issues in RL fundamentally is different from those in supervised learning. Like in RL, all the practitioners, they might not call this flat gradients, but they're all very concerned about this lack of, you could interpret this as a lack of exploration. While in supervised learning, when we go to, when we put our practical hats on, we almost never care about these flat gradients, at least not to the extent we do in RO. Okay, so the talk is really going to be trying to get a handle on when these things both converge globally and when they can handle the problem of having a large number of states and actions. And these are tricky because these methods, even in these toy problems like this robotic, this maze task, even in that toy problem, we'll see it's actually a non-convex optimization problem. And by all means, feel free to ask questions, but we're going to be jumping into the meat of things pretty soon. So the way we'll set things up is, before we go to the case of dealing with generalization and harder problems, let's start with trying to understand what's going on in small state situations when we get exact gradients. Okay, let's just try to understand what's going on with gradient-based methods in the case where we don't have to deal with the fact that we have a large number of states and actions. And let's forget about sampling too. Let's just suppose an oracle gives us these gradients exactly. Okay, then once we have the basics under our belt, now let's try to ask what happens when we look at these high dimensional problems. The ways people actually use them are not these little toy maze tasks. They're these very challenging problems with possibly continuous states and continuous actions, sometimes even in high dimensions. Great, and then time permitting, maybe I'll return back to some of the broader issues for how we study RL and how policy gradients fit into this picture. This will really depend on time, and by all means, I'm happy to take a few questions along the way. So let's just start things off and look at the case of a small state space and what happens if we exactly run gradient descent. So the first question we can ask is, like, let's write down this algorithm formally. What's the policy class? Okay, so the simplest way to parameterize the policies is, let's make them stochastic, because that makes them differentiable. So let's think of the world as having a finite number of states, a finite number of actions, and the class of policies we're going to consider is the softmax policy class. And by that I mean, for every state and every action, we're going to have a parameter associated with that state action pair. You can think of that theta as like an energy of taking that action in state S. Okay, and then we're going to write down our probability as this normalized. We're going to take the exponential and normalize it. Okay, so what's nice about this class is we can represent every possible stationary policy in the environment. Okay, and we know that the optimal policy lives in this class. Okay, so there's no issues of generalization at all. Okay, so it's complete in the sense that it contains every stationary policy. Okay, and a super simple question here is, let's just do gradient descent. Suppose we get exact gradients on this objective function. Does it converge globally? Okay, this problem is non-convex, but this is arguably one of the simplest settings, because we're not dealing with the fact that this policy class might not contain the optimal policy. And remember, this is a problem that we know how to solve with dynamic programming methods for these cases with a small number of states and actions, but this is really, you're going to give this as a thought exercise where, to really start understanding what's going on, let's just consider this much simpler setting where we can get gradients exactly, and we use this complete parameterization. Okay, so it turns out that with a subtlety, that rather than optimizing the value function at some start state S0, let's actually optimize a slightly modified objective function. So this modified objective function is, we're going to maximize our expected value under some starting distribution mu. Okay, so if you think about it, in this kind of flat example, we're going to start the agent everywhere randomly and then try to do gradient descent from this different objective function. Okay, and intuitively what's going on there in that kind of chain example going to the right, sometimes it's going to start near to the reward, and maybe just by chance it'll hit it and we won't get flat gradients. Okay, so our first result we're going to look at is an asymptotic one. So as long as this distribution has full support, it'll turn out that at every state, we're going to find the optimal policy. So that's the classic theorem of Bellman and Dreyfus, that there exists a policy that's optimal from every state. Okay, and what we see here is if we run gradient descent with exact gradients, asymptotically, we're going to converge to the right answer from every state. Okay, so are there subtleties here? Yes. The first question you might be asking here is, what's the rate of convergence? Okay, but it is worthwhile to note that even though the problem is non-convex, we do actually have global convergence. So we aren't actually in the limit getting burned by the non-convexity. But the issue is that, intuitively we might hope that by starting the agent sort of spread out everywhere, maybe that's kind of avoiding this problem of exploration, because it's starting near the reward some of the time, so maybe you won't get flat gradients. But it turns out that even with this modified objective function, the rate still could be exponentially slow. I think it might even be doubly exponential. And the reason is that the softmax function could get very, very flat gradients. Like for a while, it looks like one direction is rewarding, so it keeps going that way. But eventually it figures out maybe what to do in the right side of the world, and that information back propagates. And now it's kind of has to dig itself out of the hole it's gotten into by wanting to go left often. So, and at that point, the softmax it has become very deterministic. And once the softmax becomes deterministic, we get these very flat gradients. Okay, but at the very least, in this idealized setting, we aren't getting burned by the non-convexity, in that asymptotically we are converging. So, the next question is that, can we just fix this by some type of barrier function? We're trying to optimize something which, we're constrained to be in the simplex. So it's a constrained optimization problem, and we parameterize things in a certain way. And in practice, we tend to always parameterize our policies in a differentiable way, but it's hard to parameterize compact sets in a way that's differentiable near the boundaries. So that's what's kind of causing us to have flat gradients. So one natural idea is, can we do some type of barrier function to prevent the policy from getting too close to the boundaries of the simplex, and maybe that would help to speed things up. Obviously there's a trade-off here, because the optimal answer is going to be right at the boundary in general, but maybe we can just try to keep it away from the boundary by just a bit, and maybe that could help in giving us a finite convergence rate. Okay. So other questions up to here?
Can I jump in? Just some clarifications.
Yeah, go for it, Mark.
So you said the optimal policy is often deterministic. Is that, we're assuming a deterministic world here, or?
No, but for an MDP, like think of stochastic shortest path or something like that. You're in this tabular setting, the optimal policy will always be deterministic. Like at some state, even if the world is stochastic, for my long-term expected value, if I'm at some state, I'll always act deterministically, just because the world is Markov. I
see. And so by global convergence here, you don't mean global convergence in the classic optimization textbook sense. You mean converging to the global optimum here. So it's a stronger statement. Yeah,
that's right. That's right. So when I mean global convergence here, I don't mean converging to a saddle point or a local optima. I really mean, this is really convergence to the global optima rather than the sort of global convergence. So what I mean, when I say global convergence, I really do mean it's converging to a policy which is globally optimal value.
Okay, thank you.
Yeah, so I mean, just for this determinism, but like think of just a multi-unbounded problem. Even if the rewards are stochastic, the optimum policy is deterministic. It's the same kind of thing that back propagates. Okay, so now let's try to take this barrier insight and try to keep the policies from moving close to the boundaries of the simplex. Okay, what are we going to do? We're just, what's a natural barrier function? We'll add something that penalizes it for small probabilities or probabilities near to 1. And that's this KL objective. So it's a barrier function, but we're going to penalize it by is, this is our value function. And we're going to penalize it by giving it large negative reward if the probabilities become near to 0 at any state or action. Okay, so lambda here is the strength of the penalty. Okay, so now the question is, if we set the penalty in some reasonable way, can we now globally converge on this non-convex optimization problem? And can we do this at some finite rate? Obviously, when lambda is 0, we'll converge asymptotically. But if we set lambda slightly away from 0, it's clear that we're never going to get a policy that's deterministic, because that would be infinitely negative reward. So we're going to get pushed away from the boundaries. And can that help to speed up the convergence? And it turns out one can show this, that with an appropriate setting of the regularizer and the learning rate, so this is going to be a function of the final accuracy you want, that after a polynomial number of iterations in the states, the actions, when I say horizon, I mean 1 over 1 minus gamma, because that's the effective size, that's the effective time scale where you really care about in this gamma discounted problem. Okay, so in this number of iterations, you will find a policy that's near optimal. Okay, and unlike the last proof, which is pretty horrible, this is really, it's really asymptotic, and there's some insight in what's going on, but it's really an analysis-based proof. This proof is actually enlightening, because when you can really see why this barrier is helping you get this convergence to the global optima. Even though it's non-convex, you can somehow argue you're still making progress. And the fact that this thing's pushing you away from the boundary is really helping you make this argument that you're making progress and your gradients aren't becoming too small. Okay, so now at least we're getting into a regime that at least is a little more plausible, because we have global convergence, we have a polynomial rate. Now, yes, we're assuming we have exact gradients, and yes, we're only addressing the problems with a small number of states and actions, but at least in this base case, we're getting something polynomial.
Can I just nitpick that statement?
By all means.
So would some theoretical computer scientists disagree that your dependence on H and epsilon is polynomial?
Yeah, absolutely. So this is it's the dependence on H and epsilon is polynomial, but technically, if you knew the model, you wouldn't really call this a polynomial time algorithm, because you'd want to be you'd want to be log in H and log 1 over epsilon, which is a fair point. But the dependence on epsilon for value and policy iteration is basically the same. So it's log 1 over epsilon for value and policy iteration, but it's polynomial in H. So if you really want sort of these polytime guarantees that Mark is referring to, these LP approaches that really get that, and that you don't get through value or policy iteration. But so I think this is worthwhile to contrast to the classical approaches, but we should also think about the purpose of this exercise is we want to understand the base case. So then we're going to switch to the sampling case and the high dimensional case. And there we should not expect like log H or 1 over epsilon. So, if we actually wanted to solve this problem on a small MDP where it's known, we'd use one of these iterative algorithms like value iteration, or we'd solve the LP. This is really for us to try to get a handle on what's going on here so we can move to the harder cases. But it's, you know,
Sorry, I didn't mean to derail. That was just.
no, this is good. Like, I think it is good to kind of keep our optimization hats on in this exercise, because it is kind of a strange exercise we're doing, because we've got these beautiful iterative and LP approaches to solve this problem. So it's worthwhile to see what's the, you know, to take a more careful look at some of the detailed comparisons. Okay, so we fixed the first problem with this log barrier. Okay, and that's actually equal to KL regularization. Now, in practice, people do entropy regularization, which isn't quite the same as this KL, because entropy is really like, you know, it's like a pi theta times log pi theta. So entropy isn't really a good barrier function, because as you go near the boundaries, your entropy is still finite. It does give you some pressure to avoid deterministic policies, but provably you will not get polynomial in S convergence with the entropy function. But in practice, it does help a little, right? Because the entropy regularization is going to have a pi theta of A given S here times that, right? So that thing's always finite. So it really doesn't blow up near the boundaries. It's the relative entropy that behaves like a barrier. But nonetheless, in practice, the entropy does seem to be helpful. It's just not aggressive enough to really avoid this issue. And but now let's bump up a little and say, hey, what's going on? We're trying to solve this problem where, you know, we know there's a right answer at the corner of the simplexes, at the corner of the simplex, because there is a deterministic policy that's optimal. And because of the way we parameterize things, it's becoming slow near the boundaries. And what we could try to do is rather than have a barrier function that pushes us away from the boundaries, maybe we could change the curvature in our problems so we start moving more quickly near the boundaries of the simplex. Okay, and that's you know, often what we do when we think about you know, Newton's method and various other quasi-Newton methods. We're trying to change the local curvature to take bigger steps. And here we might want to do that to take bigger steps near the boundary. Right? So just geometrically, right, we've parameterized this simplex with these nice differentiable contours, and it's becoming slow as we travel into the simplex, but maybe we could have a metric that warps the space out so we travel more quickly near the boundaries. Okay, and for these problems that are on the simplex, there's a natural candidate to try to precondition the problem so we move more quickly. That's really going to be this, you know, I just give you the answer, but the natural thing to try is to try something based on the Fisher information metric. So this is like the gradient of your distribution times the gradient of the distribution transpose. What's subtle in reinforcement learning is we don't actually have one distribution. A policy isn't a single distribution, right? It's a family of distributions, because for every state, we're specifying a distribution over actions. So the natural metric to try here in this natural gradient is to look at the average Fisher information metric averaged over the distribution visited by the policy on the trajectory. Okay, and basically algorithms like TRPO and PPO, you can view them as essentially like first order-ish variants of what TRPO is, as trying to do an update like this. Okay, but for now, let's go ahead and try to see what's going to happen with this approach. So this approach makes sense even in the non-tabular case. So the idea is, you know, we're going to follow the gradient of the value function, but we're going to use this preconditioner, which is going to try to move us more quickly as our policy becomes more deterministic.
Can you repeat one more time which Fisher information matrix that is?
So this is the Fisher matrix of, so suppose we have some distribution. p theta on x. So this is a distribution on some space x. Okay, so this is the Fisher information matrix of the of this distribution. So the Fisher matrix of this is going to be grad of log p theta x times grad of log p theta x transpose, where the expected value of x is under p theta. Okay, so if you're doing a maximum likelihood problem and you're consistent, this will converge to the Hessian as you get closer to theta star. Because just this property like grad squared log p is actually equal to grad log p because the probability is sum to 1 in expectation. So, so this is like the standard Fisher information metric. It looks like a Hessian likelihood problem. But here it's just something that was a natural candidate to try because it had this stretching effect. Okay, but there are a couple of reasons why this update rule functionally is pretty interesting. So let's look at one example of what happens when we use this update rule. Are there more questions here? Okay, so I think it'll help by looking at one example of this update rule. So let's go back to the softmax policy class and see what this update rule looks like. Okay, so we're going to consider this policy class. We're going to look at this update rule, which was defined more generally for any parametric family of probability distributions or parametric family of policies. But for this special case, if you just work through the math, what you'll see is it actually looks like a soft version of this policy iteration update rule. So policy iteration says the next policy we're going to choose is going to be greedy with respect to this one-step look-ahead Q value. When you plug this thing into here and rearrange some terms, what you'll see is this really just looks like a soft policy iteration update rule, where we're going to boost the probability of some action A at S based on this exponential of the Q function. So as eta goes to infinity, in one step, this becomes the greedy update rule. But this is a pretty nice functional form because it really looks like just some kind of probabilistic relaxation. Rather than jumping to be greedy, we stay inside the simplex and do these updates in a softer way. This is a reason. This is not such a bad exercise to work through, but you'll have to take various derivatives in MDP. Okay, so now we can ask again. Let's forget about sampling and just say, let's suppose Oracle gave us these Qs exactly. Do we converge globally? And what is the rate at which this occurs? And one nice thing here is now it's starting to feel a lot more plausible that you should converge at a reasonable rate because policy iteration globally converges, and this thing feels pretty darn close to policy iteration if one understands the proof of that classical algorithm. Okay, so it's still a non-convex update rule. By non-convex, I mean non-convex in the parameters theta. But what happens? Okay, so now this result is pretty interesting in that if you set the learning rate correctly and make it constant and get exact gradients and follow this update rules, then after t steps, you're going to be close to the optimal value function to the tune of 1 over t. So if you do t updates, this is how close you are. And there's this kind of quadratic dependence on 1 over 1 minus gamma. Yeah, there's a couple of things that are interesting. Where the first one that's nice is, yes, we get convergence to the global optima. So that's certainly nice. The other thing that's pretty nice is we don't really have any dimension dependence in a sense. Like we're not dependent on the number of parameters. There's no dependence on the number of states or the number of actions. And that's pretty nice compared to the barrier function we used. Because the barrier function somehow, because we had to push ourselves away, it just introduced all of these dimension dependencies. But somehow this method, it isn't really pushing yourself away from the right answer. It's actually just trying to, the boundaries, it's actually just trying to move more quickly near the boundaries because of this preconditioning. and it's able to do so in a way where the iteration complexity does not depend on the number of states and actions. From an optimization perspective, this is also nice because it's a fast rate in the sense that, when we look at smooth optimization problems, it's nice when we get rates like 1/t. Okay, so those of us who have looked at optimization closely, this kind of makes us happy because it's the type of thing that we would like to see in smooth optimization problems, but we're getting this rate converging to the global optima. And the idea is actually, and this proof is enlightening. It's somehow remarkably short, and it looks a lot like a mirror descent analysis, even though somehow the problem isn't convex. And we don't really have any analog of this being somehow convexity in this disguise or anything like that. It just seems to, but I think that shouldn't be too surprising, because if you think about an algorithm like policy iteration, the proof of that globally converging is really not rooted in convexity. And we haven't had great successes in trying to interpret policy iteration or value iteration as a convex algorithm. So somehow, I think that's partly why this analysis looks a little mysterious, even though it's short. Okay, so the question's up to here. Okay, so at a high level, we're kind of in good shape on the kind of baby cases, in that we parameterize with the softmax policy class. If we're in kind of these small problems where we can compute gradients exactly, we are in fact getting global convergence, or convergence to the globally optimal policy. So this is nice because now we can start asking ourselves, what happens when we do not have exact gradients, and what happens if our policy class, say, doesn't contain the globally optimal answer, like it is incomplete, right? Because that's what we're interested in doing, where we're interested in solving these large problems, and we'd like to get a sense of what are the difficulties when we're doing that. And what we saw is, at least on the small cases, we needed this sort of distribution to be spread out to get convergence. And we got stuck with these flat gradient issues, which we could solve either with barrier methods or preconditioning. Okay, so a sort of point is, technically it turns out that this algorithm I could have put a mu here, but the point is this update rule results in the same policy update regardless of the choice of S0. Okay, so somehow, even though the objective function depends on where you start, this preconditioner removes that dependence. So it doesn't really matter, the starting distribution doesn't actually matter for this algorithm, provided you can get exact gradients. Okay, so now we're going to try to get some intuition about the large state space case, and when there's approximation errors and estimation errors. And before we jump in, let's kind of think about the role of this measure mu, which we needed to use at least in the first two algorithms. So we weren't actually optimizing, the first two algorithms, we weren't actually optimizing v theta S0. We were actually optimizing, even though this is what we were interested in, we saw it was better to optimize something like this, where this mu had full support. This was one of the things we needed to do to avoid this flat gradient issue. We also had to kind of penalize away from the boundaries, but at least for the first two approaches, we needed this to happen. Okay, and that intuitively is also what's important in solving that chain example for flat gradients. Okay, so I have video here, but I can't do it on my iPad. I'll just give you something anecdotal here, that in practice, we often don't train the system starting from just S0. Like in that OpenAI demo, they weren't just training the cube starting from that original configuration. They're actually training the hand to manipulate the Rubik's Cube from multiple different configurations and parameters, because that's not only important for robustness, but that's actually important for getting rid of the saddle point problem. And in practice, even though we care about our objective at S0, what we often optimize is the system starting in many different configurations. Okay, and sometimes we think about this is helpful for robustness, but it turns out it's even helpful for just getting the system to optimize anyway because of this flat gradient problem. That, you know, some of the time you're going to start the robot, you know, standing up, and it picks up the little carrot up high and gets a reward. Okay, and that this diverse distribution can help with the flat gradient problem in practice. Right, so this they call this domain randomization, but when they trained the system, they really were training on many different configurations and system states. Okay, and the way I think about this, sort of more informally, is this distribution mu, it's sort of sidestepping this issue that we often are faced with in RL, which is exploration. Like we're just going to, for a moment now, suppose we had someone who is helping us out a bit and could start the system in different configurations. Okay, and which is often how we optimize many of these settings. Now, how do we think about things like how do we think about this distribution mu, and how well does the what happens in the non-convex case? Let me just jump to some of the statements. You look at the slides for the prior work. Okay, so what we're going to look at now is a policy class which is parameterized by f theta of SA. So that could be a neural network, for example. Okay, so we started this special case where it's complete. So f theta of SA was a separate parameter for every state action pair. The second most natural example is this log linear policy class, where rather than having a separate parameter for every state action pair, suppose we have a feature function associated with every state action pair, and this function f was linear in these features. Okay, and this is helpful when d is much less than the number of states times the number of actions, because that helps us with the recursive dimensionality here. And of course, this function f could be also, it could also just be a neural network. That's often what we use in practice, but it's more helpful for us to start with this case where, you know, this already has a number of challenges, because we might not contain the optimal policy in this policy class, right? And we already and this policy class allows us to have far fewer parameters than the number of states and actions. And these are all like, just, you know, consider just using the top layer of some neural network. What happens there if we optimize our policy by only optimizing the top layer of the network? Okay, and now let's just focus on this natural gradient method, where we're going to try to move more quickly on the boundaries of the simplex and try to get a handle on what happens for this special case of log linear policies. Okay, so the policy class is this. So a chance of doing action A and S is log linear in the features phi. We're going to consider the same update rule, but now we're going to have to manipulate this this update rule for this policy class. I'm not going to show you the derivation, but it's not actually too bad to take these derivatives, do this inverse. And if you think about it, you can kind of guess it might have a very similar form to what we had before, where it does also look kind of like a soft policy iteration update, but it does that with approximation. Okay, so this update rule here is getting me equivalent to the following two-stage procedure. Okay, so first, what you're going to do is, you have some, there exists some function q theta, which is the q functions of your current policy. Suppose we did a least squares to fit the best q in the span of these features. Okay, so this is a quadratic minimization problem. Suppose this is the on-policy distribution starting from S0, A0 from U. Okay, so suppose we first approximated the q functions with these features phi. So that's step one. Then we could consider the soft update rule, which is update the policies not with e to the q, that should be an eta here. Not with e to the q, but with e to the eta times your approximated q, where you've approximated to be in the span of these features. Okay, and it turns out that this update rule and this update rule are equal. Okay, so this is a pretty interesting update rule because it's a lot like policy iteration, except now we're not using the exact q values, we're using some approximation to them. And note what's nice about this update rule is we can actually do a regression with samples we get to estimate this W. Because now we're getting into both our machine learning land where we have a policy class and we can use sample-based optimization. So I just said that we can consider a sampling version where we take samples to estimate the minimizer of this regression problem, and we update our policy with in a sample-based way. Again, obviously, you're not going to store this as a table. You're going to store the parameters, but this is an equivalent way the policy gets updated. Okay, it turns out you're going to store the parameters theta, but the policy itself is updated in this manner. So let me just end by, really depends how much time we have. We got about 5 minutes, so I can at least give you one of the theorems for this special case of doing this natural gradient update rule, which it does make a lot of sense for the simplex, for these stochastic policies, and arguably the simplest parametric policy class, which is where we have these features phi. Okay, and we're going to deal with the case where we might actually have estimation error. Okay, so for now, let's actually suppose that if we did the fit exactly, we didn't have any error. So we're not going to have approximation error. Let's just assume the only source of error we're getting is coming from the fact that when we do this fit, there's some statistical error. And what I mean by that is this is the error when we fit according to the current trajectories we get under pi. And this you can do entirely in an on-policy way. We just roll out the policies and we can get estimates of this on the states and actions we visited. We can just do a regression, and this is going to be, order D over M, where M is the number of samples. This is just the usual regression guarantee. Okay, and let's suppose for a moment that our starting distribution mu, because we have the starting distribution, that actually gives us a well-conditioned feature matrix. Okay, and that's going to be the surrogate for exploration. So we're not using S0, but our starting distribution is not super flat with regards to the features. So somehow we're getting information about how the features vary in our problem. Okay, so for this special case, it turns out we also get a convergence to the global optima, but there's a couple of notable changes. So now our rate is 1 over root t. So after t iterations, we're off by this amount. Okay, so after t iterations, we're off by this amount. But the second term is interesting because A is the number of actions, and H is 1 over 1 minus gamma. But the new interesting dependency is now it depends on this condition number kappa. And that is interesting because that's like our exploration that we need a start state distribution such that these features have some variation in all the directions. And we are off by our statistical error. So every round we're going to do a regression. You can think of this guy as, you can think of this thing as order D over M. If M is the number of samples we take during each epoch. But for this theorem, we made this very strong assumption that along the path of our optimization algorithm, this Q theta is a linear function in phi. Okay, so we're making this realizability assumption that these features can perfectly approximate the Q theta. Okay, and the only source of error is really coming from our statistical estimation error. But this at least is one picture of how we handle both optimization challenges and estimation challenges in RL, because this estimation challenge is of dealing with a large state action space. When we address this would be if our features could actually approximate Q theta, then we're in good shape. Okay, and we had this starting distribution that gave us variation in all the features, then we get a reasonable convergence to the globally optimal policy. And now, just given time constraints, I'll just mention a couple of things in words, but I'm happy to take questions about it. You might ask, what's the dependence on the approximation error now? Because in supervised learning, we often think of these agnostic settings where we don't necessarily assume that the optimal answer is in a function class. And here we had the strong assumption that every policy pi, its Q function can be perfectly approximated by this phi. Okay, but in the case where, I'll just jump to having approximation error and just state the result in words, and I'm happy to take questions on this after. The statistical part was really just how different our minimizer was from the best minimizer. Okay, the approximation error, what's going to be subtle here is the approximation error is going to be, we'd like it to be 0. This is the square loss. But the dependence in our theorem on the approximation error is actually really related to transfer learning. I'll just state this in words that it's a subtle way of thinking about things, but the issue is that we're fitting our Q functions under the distribution we visit with respect to our current policy. Okay, but the error that matters in the convergence rate is the error under a different distribution, which is the distribution, say, where the optimal policy tends to visit. Okay, and these sort of density ratios are what comes up in transfer learning, that if you have low error one distribution, what is your guarantee under a different distribution? Okay, and there are many people who have sharper ways to write this, but the effective approximation error is what you're paying is not just your approximation error under your current distribution. What you're really paying is, you fit something on your current distribution, but what really matters is what's your error under a shifted distribution. Okay, so I'm happy to take some more questions, but I would argue that this factor is really why RL is somehow challenging, is because even if we fit under a current distribution, what we care about is how well we do under a different distribution. So there's one question. Let me just go ahead and end the talk now, and I'm happy to take some more questions. Okay, so at a high level, we're really getting a handle on some of the optimization foundations in reinforcement learning, both with regards to convergence to the globally optima, and more subtle issues about dealing with high dimensional problems and the effects of approximation errors. Okay, and this is really one of the reasons why these methods are effective, is because not just their their convergence properties, is the ways in which they handle the approximation error. And that's definitely a more subtle issue in reinforcement learning. Okay, and one of the things we did not address with these methods, which practitioners do lots of heuristics, is how to get this good starting distribution, or how to encourage the agent to explore. And finally, I'm going to thank some really talented colleagues like Alec and Jason, who I've been working with for quite some time, and Gaurav, who's really a terrific student at UCSD. And we've been writing a book trying to put various material on just a lot of the basics, RL for really targeted graduate students and researchers. And it's kind of coming together as we proceed. There's going to be a number of updates this term. So, so thanks a lot, and I'm happy to take some questions.
Okay, thank you very much. So if you want to ask a question, you can type in the chat or raise your hand or be brave and yell out. But if you're yelling out, maybe wait until the raised hands are done first. So I think we have Victor first.
Thanks a lot. It was a great talk. Thanks for that. And I had two questions, but one of them you just answered in your slide about mu, because we just saw the influence of mu now at the end. And I was just wondering if there is anything better than just choosing the uniform distribution at the beginning, because if you don't have any extra information, I guess this uniform distribution is the best one, right?
Yeah, so the question is, if with lack of better information, what's the distribution to pick? Yeah, uniform, I mean, obviously that's unrealistic for large problems because this density ratio is terrible. But in practice, we know that transfer learning works much better than worst case theory suggests. Like, part of the issue I would argue here is if you just forget about RL and, look, we train on ImageNet, it works well on other distributions. These other distributions are not sampled from the same distribution. Okay, it's not perfect, but it's far better than worst case theory. So conceptually, without more information, what we really want is something which helps us generalize to where the optimal policies distribution visits. Which we don't have, but we sometimes have prior knowledge where that might be.
And just a second quick question, and it's a bit more technical. You mentioned that the policy gradient can be analyzed in a mirror descent way, but is it because the policy gradient can be seen as just an instantiation of mirror descent, or just because I guess they're not usually the same thing, but maybe in this case there's a mirror map that is the same thing as.
Yeah, that's a really good question. I think people have been looking at this for a while. Like, is there some convexity in disguise that we could somehow say that this really is mirror descent in some parameterization? And so far we really don't know. So the natural candidate would be, so there's this dual characterization of solving MDPs with an LP, which is you parameterize by the state visitation measure, which is how often you visit state action pair. And there you could actually do so gradient descent on that is actually doing gradient descent on the distribution over state action pairs you visit. So this is really the dual formulation. Now you could say, like, look, what if I did mirror descent on that set of variables and look and see if that matches the trajectory taken by this algorithm. And it turns out that's not the case. This is really, I mean, that's a bit more of a subtle point, but I view this as really more like some kind of experts algorithm. Like, okay, so I view this really as the analog of soft policy iteration. And policy iteration, you can view this as like a block simplex method, but it definitely does not like anything convex. So somehow the analog for me is this is really a softer policy iteration algorithm than any analogs of the convex approaches.
Very interesting. Thanks a lot.
Maybe Sham might disagree with this comment, but I believe that people have tried for more than 50 years to come up with a Lyapunov function for what like policy iteration does, and have not been successful at that.
Yeah, so I'm not, okay, right. So I'm not strongly, wait, so you're arguing that we don't have a convex interpretation of policy iteration. Yeah, so that I for the most part, I agree with that. The only exception I would say would be this kind of like seminal result by Yin Yu Ye, where he proves for a fixed horizon factor, policy iteration is strongly polynomial. This was like a huge result. And the way he did it is he made some connections to a block simplex algorithm. So you know, as far as I'm concerned, like that result's pretty amazing. I'm not a combinatorial like algorithms expert, but I think that is one of the most interesting connections between policy iteration and a convex approach. But yeah, I largely agree with your comment.
I'll have to get that reference for you. That sounds super interesting. Michael, do you want to go ahead?
Yeah, okay, great. Yeah, no, thanks. Thanks, I really enjoyed the talk. I'm coming at things from a perspective of making robots move and controlling locomotion and a variety of things. And so a lot of the points that you emphasized from the theory perspective actually really rang true to me on the ground, so to speak. But so there's one thought that and related to choosing the initial state distribution mu, that where the intuition on the grid world that if you start from many states there, including ones possibly close to the goal, that the larger initial state distribution made the problem easier in some sense. But in many other problems with continuous state distributions, it can also make it much more difficult, right? Because the fragile solution for an OpenAI gym problem, from a deterministic initial state or from even kind of a lot of the OpenAI gym examples introduce just a little bit of stochasticity in the initial state distribution. And it turns out if you increase that, then the problem it actually becomes more difficult to learn is what we found. And to some extent that makes sense, because you're asking it to basically to recover from a much wider range of configurations. And so anyhow, that it seems to me that it's interesting that it's difficult to make a statement about is larger mu easier or more difficult, and even there I can think of examples that pull in either direction. Any thoughts on that?
Yeah, okay, so it was interesting about trying it. So because this was, if I did it, I was doing this with PDFs, but I had videos for this kind of showing your point about robustness as well. That so the question is like, more broadly, there's this relationship between the distribution mu and possibly robustness, because like these OpenAI things, you optimize from a given starting configuration. But in real applications, we don't just want it to do well from the starting configuration. We'd like it to do well under little perturbations or starting at slightly different configurations too. And there may be an interplay with the choice of mu. And so the first point I make is that, in fact, this issue of like distribution shift and robustness, they're really two sides of the same coin in RL. That some of the issues we face in getting the policy to be robust, it's almost the same issue in just getting it to optimize in the first place. Okay, and in terms of the choice of mu, I'm going with there not being a major trade-off here. I would argue there's a representational trade-off, that to get it to work on a more diverse set of mu, then we want a better representation. But I would argue that like the way that they're solving this thing is the way you're initializing it is you're not just initializing it kind of close to the end state, you're initializing it in regions you think you might get perturbed to as well. Okay,
sure, yeah, that makes sense if indeed you know that, but
if you know that, that's
a bit
right.
of a chicken and the egg problem.
That's exactly right. That's right. And that's kind of where, these MPC approaches are great, that on the fly they can do things, but like in a sense, part of this issue is that why I view this as like a transfer learning problem. I'd like to know the distribution I need to optimize under, and you don't. But if my feature is allowed for transfer learning for there, great. But yeah, I think this is, I completely agree. There's a bit of a chicken and egg problem, but the thing I wasn't gonna, that I didn't have time to discuss was, this approach largely took something like in the supervised learning analog, you would call this an agnostic learning setting, that where, like forget about RL and robotics for a moment. Think of like image recognition. We train on one data set. If we get samples under the same distribution, we do well, fine. But a lot of times we deploy things in settings where our distribution is actually, it's not representative. And it still works reasonably well. We just don't understand why this is the case, aside from saying our features are good, but there's obviously like approximation error. And that's, I would say, the fundamental issue when we start dealing with these robustness issues. And when we make more structural assumptions, yes, we can prove all kinds of things. The problem is those assumptions just tend not to hold. So, I think these are great questions. They're hard to, I think each problem is going to the cookie's going to crumble in a bit of a different way.
Yeah.
But,
Sure.
but yeah, these are, this is a really great question. I think it's the right one too. Just trying to get a sense.
And just very quickly, if I might, so yeah, any thoughts on curricula? Just because this also fits a little bit into the same scheme of things, because you are changing the MDP by kind of changing the initial states, and so there's a lot of other ways in which we might change the MDP to make to facilitate the learning, and so yeah, including like task curricula, starting with easy tasks and going to harder ones, and the initial state configuration is maybe belongs to that class as well. But you might start with an initial state close to your goal state, and then gradually move it further away.
Yeah, so curricula is like certainly a great the sort of a talk 2 version, which is more about representation, that something I've been thinking about. But the curricular learning strikes me as interesting for 2 reasons. There's reason one, which I think we do have a good handle on, which is more this imitation learning setting, where we can kind of see where an agent should go and maybe match the trajectory. And or if we had a curricula where you could, someone could roll in under a good policy and then let the agent behave. And the kind of ideas here really support curricular learning pretty solidly. There's kind of version 2 for me, which is a little more speculative, but I think where it could really shine is that often in the world, we're not trying to solve one problem with one objective. And, learning on one task actually helps us on other tasks. And we don't know the way in which the types of representations transfer between, say, different objective functions. And that's the type of thing where, I think curricular learning can clearly help, like playing Atari games and stuff like that. Like we play one, it helps us with the other sort of thing. And, in robotics, there are certain types of, physics-based representations which are helpful. And once we start pinning those down, they might help in like many different problems. And that's something more about that's something more about what constitutes a good representation for these things, which I think is a pretty interesting direction for curricular learning that is relatively.
Sure. Great, thank you.
Thanks.
Okay, Wilder, do you want to go ahead?
Sure. First of all, thanks for the talk. This was really informative. I had a quick question. Oh, can you hear me?
You're muted.
You're muted, Wilder.
Am I?
No, maybe not. You're just very quiet.
Yeah. Oh, this is actually
Still very quiet.
Can you hear me?
Barely.
Okay. Well, sorry. I don't know why this is not.
Fred, why don't you go ahead, and Wilder, why don't you type your question into the chat?
Hello to Echo Wilder. Thanks for the talk. It was really nice. There's a question I have on the discount factor. This might be very basic because I'm not that much deep into reinforcement learning, but the vanishing gradient issue seems to be, and the fact that we need exponential time to get there seems related to the fact that we have a geometric decrease on the value ahead, like the multiplication by the gamma factor at every step. Is there, like, if we change the discount factor and instead of like gamma to the t, if we use a 1/t², that still converges, does it fix some of those issues?
Yeah, okay, so right. So the question is sort of what's the effect of the discount factor? So on this, on this flat gradient issue. So that really isn't, because there's certainly the fact that we care about a reward over some future horizon that is definitely related to this. But the fact that that's decaying geometrically, that really isn't the issue. See, the issue is that in that time horizon, our gradient is really flat. Like the same issue comes up if we wanted to optimize the undiscounted sum of the future reward in the next 50 steps. Okay, because that thing, there's no discounting at all. What happens is that over the time horizon, if we aren't getting anywhere near to where we're getting the reward, then we get flatness. Because see, if the discount factor was decaying extremely quickly, we'd be fine because we don't care about the future. Right? The discount factor that's relevant here is, suppose we have a 50-state problem, and a discount factor is like 1 minus 1/50 or something like that. It basically is undiscounted over the first 50 steps. Okay, so so in a sense, like the technical details of this are that, we're looking at the regime where effectively the discount factor plays no role here, because that's the kind of relevant time horizon. It's the fact that we just aren't getting the rewards when we act randomly in that time horizon.
Okay, Jesse, do you want to go ahead?
Yeah, thanks. This is a very general question, but so these are really powerful techniques. So I'm an economist, and a lot of what we do is we'll solve kind of dynamic programming problems. We have in mind kind of trying to solve an approximation for what agents might do in the artificial world that we create for them to try to understand things. Now the model-free model-free methods are very powerful, that you don't have to specify the model. But on the other hand, in other times, the world is just too complicated for these agents to learn from observations. So I know this is a very rough question, but is there anything that you can do kind of in between this model-free world and sort of the classical setup where you carefully model the Markov decision process? Can you have it both ways? In robotics, is there any research on that?
Yeah, so the question is partly like, these approaches at least can be implemented in a model-free land. And, maybe if you had more information, could you actually build a model or utilize it? And look, the drawback for the model-free approach is it's kind of polynomially-ish sample efficient, but it's not as sample efficient as it could be because you're throwing away the previous rounds of data. And that could be helping you quite a bit. And
there's also so to people like me, there's another thing, which is that you're not building abstractions of the world into the agent's decisions. So on one side, it's you're throwing away data. On the other side, there are things that you know as a modeler or that an agent in that world might already know. Yeah.
Okay, so there's the in-between of like the abstractions, and I would view the abstractions as relevant both in the modeling land and the model-free land, because let's take this analog. So the reason I'm talking about sample efficiency, let's take this analog in the supervised learning setting. So there, the abstractions really are coming in our neural network. We're trying to learn the abstractions as we proceed. And when we parameterize these gradients by neural networks, we're also trying to learn it. And when we don't put interaction in the mix, I would say the jury is leaning pretty heavily on just run your neural network, it seems to learn the abstractions. And there's often crude information that helps, but the more a human tends to tinker with prior knowledge, it often doesn't help. Okay, but once we go to, I think, the interactive setting, then it is a lot more subtle because of this issue that if you act randomly, we don't gather the information. And there, I think that's where really things become interesting. And the way Rich Sutton puts it, he's one of the kind of founders in this area, but he had something called the deadly triad, which was sort of a function approximation. So that's putting neural networks in this thing. Temporal dependencies, which is your long-term horizon, and kind of the thing you want, which he calls bootstrapping, which is, so you have, I'm estimating these gradients only with rollouts under my current policy. Okay, but I have all this previous data, what I've done in the past. Could I build a model or bootstrap off of the information I have in the past to help my current estimation and maybe use less data? And that's where things become actually pretty hard because and this is, I would say, one of the fundamental challenges. Like machine learning does extremely well in the non-interactive setting of supervised learning. But once we start going to these interactive settings, while it does well, the sample efficiency is hard. And the issue there is really, what I would put the medium is about extrapolation. And we kind of want to extrapolate in regimes where maybe we don't have to build a full model, but and that's like, this is a very real question. And there is work on trying to do what they call like off-policy methods. That's sort of the buzzword right now, which is trying to understand what type of kind of representations of the world actually support methods which can work where you've collected the data according to a different policy. So there's a lot of nice work in this area from like people like Emma and like healthcare people are using. It's not quite econ, but there's a lot of overlap in econometrics and like.
Okay, that's great. So this is off-policy methods is kind of the
keyword. Off-policy or offline RL is probably the keyword, but offline RL and people like Emma Brunskill, Susan Murphy, Finale Doshi Velas. There's a number of people that have like very nice work in an area called offline RL, and they're looking at this. And as you imagine, it's subtle because you're trying to figure out the effects of like treatments over multiple stages with offline data. And now should you build a model for this? Like how do you evaluate things? This comes up also a lot actually in like supply chain things too at real companies where they have a lot of offline data and they want to try some sequential decision-making strategy without running it. What are the challenges we face? And yeah, you have this very real tension between building a model or trying to, be more relaxed about it.
Mm-hmm. Okay, thank you so much. That's very helpful.
Okay, we're just gonna end with Wilder because we need to stop at some point. Wilder, do you want to try and ask your question live again, or
can you guys hear me now?
Yes.
Yeah.
Okay, wonderful. Sorry about that. So yeah, thank you for the talk. I really enjoyed, especially the first chunk of it and the explanation for log barrier functions. My question was if you scroll back, I think 2 or 3 slides to the way that you split up the epsilon error into estimation and like I think under parameterization. In that setting, is at least the under parameterization epsilon? So is there, or do you know of any algorithms that are actually actively targeting, basically imprecise estimates of the Q function? Also, the split there is really nice. It's very cool.
Yeah. So okay. So if I understand the question broadly, is like what are algorithms which target kind of this this approximation error? So one thing, yeah, the split is nice. The frustrating thing, but maybe revealing, is that the way you depend on the split, it's very, it's pretty painful in that you have a model dependence on the amplification due to statistical error. That's really just coming from a conditioning number your, you just need your features to go in all directions. Okay, the way we're paying for the approximation error, which is really just the square loss compared to the best thing on the current distribution, is really coming from distribution shift. And if anything, this is getting like maybe back to curricular learning or deep learning, because these are really questions about how do we train on one distribution in a way that extrapolates. And we do not have a great idea of how to do this in machine learning. There are like various settings, but it's a hard question, because what we really want to do is, so it's not as stringent of just saying, hey, we want to have a low approximation error, because it's never going to exactly be zero. Like what we want is something a little more mild. We want, let me phrase it this way. So if we didn't have to worry about distribution shift, we don't worry about approximation error in machine learning. These neural networks, they seem to drive the approximation error down pretty darn small. Okay, but the point is, it's small on average under a current distribution. Right, that's the issue, that we know how to make approximation error small under the current distribution. But the problem is, once that distribution changes, it might have, the average case approximation error is good, but what we care about is sort of the approximation error in some type of extrapolation regime. And that is a pretty, I think a lot of the questions here, the econ question was kind of related, partially related to this. The curricular learning one was, and what we're seeing now is in RL, we really need representations that somehow are, what I would argue is robust to distribution shift. Okay, and that is an active area of work, but I think both technically and conceptually, we need new algorithms and new ideas here.
Cool.
But at least we see kind of why it's important. Like what's interesting here is, see, normally in supervised learning, like the like language models and such, like, yeah, like it's fine on the current distribution, but when we deploy it, we have a different distribution. What's interesting here is it's relevant on the problem of interest, having sort of this low transfer learning error. Because why? Because the problem of interest is an interactive one. It doesn't come with its own distribution. So somehow to solve the problem of interest, we kind of also have to address this issue. With supervised learning, it's almost like a two-phase thing. We do well on the current problem, but at deployment time, we want to do something different. So here it's kind of all wrapped together in RL, and yeah, I think it's an interesting open direction for how to make progress here.
Yeah, I mean, it's great seeing it there, like having a formal mathematical thing for the term that's embarrassing a lot of deployed machine learning systems.
Yeah, that's right. And what's interesting here is it comes up in the end of optimization of the thing we want. Whereas in supervised learning, it's embarrassing that we optimize on one distribution, but we deploy it and it's kind of different. Whereas here, even for the thing we care about,
here's the ratio that makes your algorithm racist type of thing.
Yeah, that's
okay, let's thank the speaker again. That was fantastic.
All right, thanks for having me.
Thank you.